Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Well, possibly, the flap of a butterfly's wings in Brazil can set off a cascade of atmospheric events that, weeks later, spurs the formation of a tornado in some other location. The butterfly effect refers to the phenomenon when a small change in starting conditions can lead to vastly variable outcomes, and is used to explain why, in practice, our ability to make predictions for nonlinear systems is limited because we can never know the exact value of the original conditions. Even slight errors in measuring the state of a system will be amplified dramatically, rendering any prediction useless. The butterfly effect, also known as chaos theory, is illustrated by the double pendulum, because small changes in the initial conditions of the pendulum results in drastic changes in the trajectory of the double pendulum.
Why do double pendulums exhibit this behavior in contrast to single pendulums? The motion of a single pendulum is predictable and ordered, regardless of how initial conditions are changed. You can predict its motion using information on its acceleration and angular frequency. At small angles, the pendulum executes simple harmonic motion, whereas acceleration is directly proportional to its displacement and is directed towards the equilibrium position. At large angles, the motion is no longer simple harmonic, but the motion is still ordered. The double pendulum is composed of a second pendulum attached to the end of the bob of an initial pendulum. Since there are now two angles, θ1 and θ2, changing with respect to time t, this system exhibits 2 degrees of freedom. As a result, the motion of the pendulum is more difficult to model and requires more complex mathematics than those used to stimulate the motion of the single pendulum. We created a double pendulum using a 3D printed model. The motion of the double pendulum is completely different from the single pendulum. It is highly sensitive to initial conditions, where even the slightest differences in angles between the release of both pendulums will lead to a huge difference in the pathways. While it is possible to derive the equations of motion for the double pendulum, it is impossible to predict the path the pendulum traces due to the large number of unknown variables and the butterfly effect. Moreover, due to the uncertainty of the precision of instruments used, it is impossible to get an accurate measurement of the initial variables, making it also impossible to predict the path of the double pendulum.
At small angles, the pendulum will exhibit an ordered motion with periodic beats as it sways from end to end. These beats can be seen through the difference in displacements of the two arms. The arm at the bottom will displace at a larger angle than the arm at the top. Now, let's examine the motion of our double pendulum when we change the angle at which it is released by a small amount. This is denoted by the blue lines which follow the motion of our double pendulum. Likewise, the motion remains chaotic and unpredictable, showing no form of patterns or any distinct period for that matter. Now, let's look at an overlay of these two motions to help demonstrate our topic on chaos theory. As we look at the two motions, we notice that they become very different even though there is only a very small difference in initial angle. This emphasizes how a small change in initial conditions can lead to a very drastic difference in result. In this case, the motion no longer bears any resemblance to one another.
Now let us derive the equations of motion for the double pendulum. Here, x1 and y1 stands for the x and y coordinate of the center of mass of the first pendulum, and x2 and y2 stands for the x and y coordinate of the center of mass of the second pendulum. Θ1 stands for the angle between the vertical and the center of mass of the first pendulum. Θ2 stands for the angle between the vertical and the center of mass of the second pendulum. Here, using a bit of trigonometry, we can actually express x1 and y1 in terms of theta, where x1 is equals to L1 sine θ1 and y1 is equals to negative L1 cosine θ1. We can also do the same thing for the second pendulum, where x2 is equals to L1 sine θ1 plus L2 sine θ2, and y2 is equals to negative L1 cosine θ1 minus L2 cosine θ2. From here, we can actually find the velocity of both the first and the second pendulum by using a bit of differentiation. So the derivative of x and y with respect to time will actually give the velocity, where v1 square will be equals to x dot 1 square plus y dot 1 square. And likewise, v2 square will be equals to x dot 2 square plus y dot 2 square. And if we use the equation for kinetic energy, half mv square, we will derive the equation for the kinetic energy of the entire system as a whole. Likewise, we can also derive the GPE of both the first and the second pendulum using the general formula mgh, where the GPE of the first pendulum is given by m1gy1, and the GPE of the second pendulum is given by m2gy2. Now, after we have found both the KE and the GPE, we can actually calculate the Lagrangian, which is based on the principle of least action. The Lagrangian can be calculated by taking the difference between the kinetic energy, T, and the gravitational potential energy, V. By doing so, we can calculate the Lagrangian and insert it into the Euler-Lagrange equation, which tells us that d over dt dl over d theta dot I minus dl over d theta dot I is actually equals to 0. With this equation, we can actually calculate the individual terms in the equation. We can do this for both theta 1 and theta 2, where the expressions for dl over d theta 1 and d over dt dl over d theta dot 1, as well as that for theta 2, is given by these four equations here. After inserting this into the Euler-Lagrange equation, now we can actually find the two non-linear differential equation that describes the motion of the pendulum.
What are some applications of the chaos theory we see in real life? The application of chaos theory to the physical and chemical sciences has resolved some long-standing problems, such as how to calculate a turbulent event in fluid dynamics, or how to quantify the pathway of a molecule during the Brownian motion. For Brownian motion, we observe the motion of smaller, finer particles colliding on a bigger particle. From the trace paths of the bigger particle, we notice that they appear to be random and unordered. However, chaos theory can actually be used to resolve and quantify the paths of these molecules. The double pendulum is also an example of how we see chaos theory in real life, where the double pendulum models the human arm. With research conducted on the chaos motion of our arm,